Welcome, everyone. I hope the countdown worked okay. It didn't seem to be working fine from my part, but the SP technical section for well integrity and P&A are pleased to present this webinar today titled Understanding and Managing Sustained Annular Pressure. My name is Pierre-Edouard Vincent, and I will be your co-host. This event has been scheduled for roughly an hour, but will not have a hard stop. We encourage you to ask questions throughout the event. For this, simply create comments from the platform you're using, either LinkedIn or YouTube. Before we start, I would like to announce a few of the upcoming events related to well integrity and P&A in our region. First and foremost, one of the best event on the European scene when it comes to well integrity. This is the a workshop in Amsterdam in the Netherlands on the 11th and 12th of November this year, co-chaired by Michelle Monto with Aker BP and Kenny McAllister with Seal Tight. It will be followed, I'll put a link in the chat box, it will be followed, though it has no connection, by one of the first conferences on offshore methane emissions in an OC, which will be in Utrecht, jointly organized by TNO, SODM, and yours. And this should be quite interesting also. But it's now my pleasure to hand over to my co-host and fellow WITS officer, Jovan Stojkovski. Jovan, over to you.
Thank you, Pierre. We are all welcomed Andrey Yugay, who is a graduated mechanical engineer and started his career in 2003 with the well service department of Schlumberger. After 4 years with Schlumberger, he worked in the coil tubing and cementing teams in Kazakhstan. He moved to Egypt, ENI, working as a completion and intervention supervisor. He was one of the first focal points assigned for the well integrity business of Kashagan field, currently operated by NCOC. In the 2013 to 2014, he spent some time with the PDO Oman as a world service supervisor in testing department, and eventually joined ADNOC Group 11 years ago. He holds the position now of Senior Well Integrity Specialist in the Group Asset Integrity Department of ADNOC, and his main industry achievements are published in significant 17 SPE papers. So you can meet Andrey on upcoming technical conference on well integrity as a technical committee on AIMCS Expo 2026, which will be held in May in Abu Dhabi. And thank you, Andrey, for sharing your work and experience with the SPE community. This is really significant number of SPE paper. We wish you continue like this, and thank you for having us together here to talk about understanding and managing sustained annular pressure on the wells. Andrey, the stage is yours.
Thank you, Pierre. Thank you, Jovan. Good time of the day, dear audience. So the subject we are going to talk today is about SAP well. SAP stands for Sustained Annular Pressure. It's unlikely that I may say something new to the audience, but maybe I will try to change your approach, to improve your approach in managing those SAP wells. Okay, so let's start. This webinar is sponsored by SP International. This is our agenda for today. It's not much. We're going to review a double barrier policy. We'll look at the SAP management steps, and we'll talk about a little bit about the basics of the risk assessment. So we know that all wells that can flow naturally, wells with a positive pressure at surface, should comply to double barrier policy. Yes? There is a primary barrier envelope, the one which is in a direct contact with hydrocarbon, or the one which is continuously under pressure. And then there is a secondary barrier. So if primary barrier fail, the secondary barrier is supposed to hold the pressure within the confines of the wells and prevent further escalation. So looking at this nice Spartan warrior, what we can say that the shield he holds is his primary barrier, correct? That's the one that will take the the impact of the strike. And then if he loses his shield, then his last line of defense will be his armor, correct? But what he's going to do first thing after the battle is finished, if he survives, inshallah, he's going to find his shield. He's going to restore his shield. So he will be ready for the new fight, new battle, correct? Arguably, we can say that the sword can be also used as a defense, but that's not the main subject today, okay? Mainly it is used for attack. So what is the message I want to pass here? That obviously the guy, he wants to survive. He wants to return back home alive. Yes, he wants to live. And definitely he would take care of his armor and of his shield. He has a very big motivation to take care of it, correct? And obviously, he doesn't want to fight the battle with single barrier only, correct? So the message here is that sometimes people think that if one of the barriers is still available, they are absolutely safe, which is not always true, yes? But today we will talk about when it is true, when it is not true. So now coming back to our business, yeah? So on the left side, you can see the picture, a representation, illustration of double barrier policy. So we have primary barrier envelope, the one with the blue color, and the one in red is our secondary barrier. Same with the well. Yes, whatever is in direct contact with hydrocarbon, whatever is continuously under pressure is our primary barrier. If primary barrier fail, tubing leak or packer leak, then secondary barrier is our last line of defense, okay? If the secondary barrier fail, we're going to have a well control incident in the production phase. We're going to have well blowout, which is something that well integrity should not allow to happen at all. That's our role. Unfortunately, sometimes it happens. When I'm talking about secondary barrier envelope, mainly I'm talking about the condition of our casing. Because, for example, yeah, wellhead equipment is also part of the secondary barrier envelope, but it has quite a strong, big design factor. Yes, the thickness of the wellhead is much higher than the thickness of the casing. And casing can degrade, casing get corroded. Mostly casings are made of carbon steel, and carbon steel is not a stainless steel. It's not a CRA alloy, so it can get corroded. It can get corroded externally, as you can see on the pictures on the left side. This is external casing corrosion due to high salinity, exposure to oxygen. It can corrode in between two casings. That's what you can see on the right side on the log. What we can see here is a MVRT log of Baker Hughes. On the most left log is our discriminator, which we can see there is a hole, and then the flux, the main sensor, shows that there is a massive external corrosion. And if we try to understand why exactly it happens exactly at this depth, on the right side you can see the cement bond log, and what we can see, this is a interface between good and bad cement. And what we know that corrosion is not just a chemical reaction, it is also electrochemical reaction, yes? So at the interface between cathodic and anodic part, we have an accelerated corrosion rate. So that's what happened. That's what triggered it. A part of something else that I will talk later. How we understand that this happened exactly in between? We have electromagnetic multiple barrier log, as you can see, column, let's say 4 and 5, where we can see the corrosion of 9958, which is matched exactly with the MBRT log. And also we can see that the 13th rate is corroded all the way from top to bottom, but the corrosion, the metal loss, stops at exactly the same depth where we have a corrosion of 9 infrared. So putting all this together, we got the puzzle. Yes, that the corrosion happened in between these two casings, 9 infrared and 13 infrared, at the interface between good and bad cement. Yeah. So corrosion can happen in between casings, and corrosion can happen internally from internal side of the casing. So look at this pressure survey. It's a wellhead pressure history of one of the wells. What we can see here, yellow line is our tubing head pressure. Ignore please this spike, it's probably the data quality issue. Look at the green line. Green line, it's our annulus pressure. What we can see that the well got annulus pressure for at 2010-11. It was bled off, it builds up again, it was bled off, it builds up again several times, but nothing was done since 2012. Only in 2019, the well was subconfirmed, investigated, endorsed for the workover, and workover was done in 2020. So we are talking about 8 or 9 years of exposure of the secondary barrier envelope to pressure and to the well media. And by the way, it was a water injector. So let's look what happened. During the workover, the tubing was retrieved in pieces. It was severely corroded, just junk, just nothing. Complete corrosion of the tubing. And the casing, all the way from top to bottom, was severely corroded internally. This is as you can see, all the way from top to bottom, different depths. This is an example. So same MVRT log, what we can see on the flux log, we can see on the sensor, we can see corrosion. However, internally, the discriminator shows that internally the casing is fully corroded all the way from top to bottom. Okay, so what is the message from this slide is that if we ignore subwells, if we ignore exposure of the secondary barrier to the well media, and sometimes it is not really designed for the long-term exposure, then we can lose the well completely. Because what happened in this particular workover, drilling team, they were so scared, that they almost do not have a barrier in place. So the well was plugged and abandoned straight away. Now, how we can control the corrosion of the secondary barrier? From outside, we can use coating. Yes, from inside, we need not to expose to the corrosive environment. What about the conditions in between? How we can prevent? You see on the right side, there is a corrosion, and this corrosion actually happened at 950 feet. Top of cement is at 950 feet, and then we got this corrosion happening. How we can prevent this, basically? Yes, if our outer casing would be coated externally, it would not help us at all. If our inner casing, 9 infrared, would have been coated externally, yes, it would help. But still, the corrosion of 13 infrared would happen. And there is currently, we don't have internal casing coating service on the market. So in order to prevent our barrier failures, we need to understand the root causes. Yes, we need to dig why it happened. So that this fluid, which is contaminated with cement, is not treated against corrosion. And this fluid is corrosive. I'll show you something now. So this slide, it's not something that we created. It's a NACE publication, okay? And NACE, National Association of Corrosion Engineers, they recognized the hazard from drilling fluids itself. For example, you know what is Pepsi, you know what is cola. You know that we use CO2 gas to make those carbonated drinks, to make it bubbly. So how much ppm is of CO2, for example, is in one bottle of Fanta. What is the concentration? You can guess. Who knows can type in the chat. I will tell you, around 6 to 7,000 ppm of CO2 is inside the cola or Pepsi or Fanta. Yeah? NACE recognized that there is a very high corrosion rate of drilling equipment and well equipment. Sometimes it's reaching, as you can see here, 9 millimeters per year. 9 millimeters. What is the thickness of our casings? It is around 9 millimeters. So imagine the corrosive rates could be so high that we can lose our casing in 1 year. Now, why I'm talking about the Pepsi Cola, what it has to do? You know what is dissolved oxygen? Same like dissolved CO2 in the Fanta or Cola or Sprite. Basically, the limit, the safe limit in the closed system for the oxygen is 20 ppb, parts per billion, okay? However, if you take any bottle of water, even though there was no oxygen there at all, once you open it, once you expose it to atmosphere, immediately you get some amount of oxygen inside, dissolved oxygen. In the water that we use for our drilling fluids, drilling mud, chemical wash, spacer, low viscous spill, the amount of oxygen is 8 ppm, but the limit is 20 ppb, okay, parts per billion. So we are talking about more like plus minus 1,000 times exceeding the maximum safety limit for the corrosion reaction due to oxygen. Oxygen is inducing corrosion reaction, and oxygen is a consumable of the corrosion reaction. So this can be controlled with the usage of chemical corrosion inhibitors, biocides, oxygen scavengers. Such kind of corrosion on the right side could be prevented if we control our fluids that get contaminated with the cement slurry and get trapped. And you know, stagnant conditions could be even more dangerous than dynamic in terms of corrosion. Now, degradation of secondary barrier. We are still talking about degradation of secondary barrier, yeah? How confident we can say that our secondary barrier are still okay? Cement also can get degraded. Recently, I had a kind of small argue with one guy in LinkedIn who says, no, cement doesn't change. Cement is quite elastic, plastic. It's just what we see is debonding. For me, honestly speaking, the main function of cement is hydraulic isolation. So if it cannot provide hydraulic isolation, whether it's debonding or micro-cracking or microannular, I mean, I don't care, correct? If it degrades, it degrades, whether it's cement or debonded. So what we can see here, same well, same depth interval. There is a ultrasonic log recorded in 2005, and it already shows cement is not really perfect, but still the amplitude is quite low. Amplitude is this red dotted line. And then after some period, in 2012, we had workover, and we repeated the same tool from the same service company. You can recognize it. We repeated in the same well and same interval. You can see there is a significant degradation of the cement, and the amplitude got shifted on the right side. So it's almost a free pipe now, and we see when there is a gas coming from the bottom. And here I want to say something. When we talk about the risks, because later we are going to talk about the risks, part of the risk assessment is a leak rate. Not only the pressure, yes, but also the leak rate. So if we measure the leak rate at surface in this well, which is a sub-B well, okay, at surface, normally, how much we get? Not much, like maybe one glass. I don't know if I can show this. I have a mug with me. So the leak rate normally is low at surface. However, if we punch a hole here in the casing, let's say at this interval, just at the top of the liner, top of this log, it might be that leak rate will be higher, yes, because all this cement, all this 9 or 10,000 feet of cement, it chokes the flow. But if we go deeper, we have less choke, so less friction. So we're gonna have higher leak rate. And definitely, if I make a hole somewhere across the gas invasion area at the bottom of this log, on the right side, you can see, definitely the leak rate will be higher than it was above the small cement ring, yes, because the cement ring works as a choke that restricts the flow. So what I'm trying to say is that, yes, it might be at surface, the leak rate is low, but if the outer casing, in our case, 13 and 3/8, for example, will get corroded somewhere at the middle of the well across aquifers or another permeable formations, the leak rate will be much higher than what you measure at surface, okay? So this is something you need to consider as well. So why I'm talking so much about the corrosion and cement degradation? Because it's a part of our cement barrier, our secondary barrier, let's say. Because you understand, if the cement get degraded, it cannot be empty. There is something in between the cement and carbon steel. Our casing is still carbon steel, eh? So in that might be a corrosive environment, and that supports the corrosion of our secondary barrier, internally, externally. So let's summarize here what we come up to. We know that if there is a pressure, we bleed it off. If it builds up again, means it's a sustained anomalous pressure, and this is evidence that our primary barrier failed, and we have a violation from double barrier policy. And it's only secondary barrier that supports the pressure. And that secondary barrier gives us a grace period before the escalation. And grace period is our period when we can do something. We can do our risk assessment, sub investigation, kill and secure the well, make it safe. Now, as I say, casing may corrode externally, internally, and in between. And there are different mitigation and prevention measures to control such kind of secondary barrier degradation. Cement can degrade with time as well. Pressure, temperature cycles, ballooning. Every time you pressure test your casing, you destroy your cement, because cement, it has a high compressive strength, 3,000, 4,000 psi maybe, if you're talking about the tail. But in tension, it's normally service provider, they take a value which is 10 times less than the compressive strength. And when you pressurize your casing, that's exactly what you're doing. You stress your cement ring in tension mode, okay? Same guy I talked to in LinkedIn, he says that the cement doesn't crack under tension because there is a formation around that supports the cement due to overburden stress, because the formation is not absolutely 100% solid, and due to creeping effect of the shale salts. So, and then I got confused because honestly speaking, if we have a creeping effect, if you have outer forces pushing our cement, then how can we get debonding? So I stopped the discussion. So let's move further. We have two warriors. On the left side, warrior number 1, and on the right side, warrior number 2. You can put in chat which one you prefer to fight if you have to fight. Imagine you are a gladiator on the arena, a Colosseum, and you have to fight. What I see here, yeah. If we want to survive, if we don't want to die, yeah, our choice would be the guy on the right side, guy number 2. Why? Because he has less barriers. Because it might be more easier for me to kill him rather than the guy on the left side, correct? So what changed? For him, for the guy on the right side, the risk of getting killed is higher, agree? So same we're supposed to do here. If we have tubing click or Packer leak, means we have a violation from double barrier policy. That means that whatever initial risk level or risk ranking or risk range, risk register, whatever you use, guys, whatever it had at the beginning when the well was healthy and having 2 barriers, now the risk level is different, correct? The risk of what? The risk of well blowout. That's what well integrity objective is, to prevent well blowouts. And when you evaluate the risk of the well, when you give her a risk level initially, obviously after losing one of the barrier, your risk level should increase, correct? Okay, so first thing what you need to do once you get the evidence that the well lost one of the barriers is to reassess the well. Makes sense, correct? Logical. Because you don't know. Maybe I have enough time to do my diagnostic investigation, presentation, study, maybe. Or maybe the situation is really critical. Maybe it's a very old well. Maybe the casing is corroded. Maybe the blowout, already there is underground blowout, I don't know. Maybe the blowout can happen anytime from now. So that's the objective of the risk assessment, okay? To reevaluate the risk. Now, let's say everything is okay. So that's my sub-well management steps. The logic and chronologies and the sequences, for me, it's quite logical, but please comment, okay? I need your feedback. So we do wellhead pressure monitoring. We discover there is anomalous pressure and it is more than 100 psi. And this is not induced. It's not gas lift well, or there is no chemical injection in the air anomalous. So what we do? We need to do bleed off, build up, yeah? BB test. Someone called BB test. We bleed off, and if it builds up again next day, that means I lost one of the barriers. So I get my well sub-confirmed. Now, sub status to be registered in the systems. That's what I noted sometimes, as per the study done by many companies, not even oilfield industry companies, people spend a lot of time just looking for the data, collecting the data within the company database. So it is very important to, let's say, to register it somewhere. And then we need to do the risk assessment. Guys, I will handle all the questions at the end, okay? So let's say risk assessment shows that the well is not critical, not high risk, and we have a grace period. So we need to do the diagnostic investigation. Why we need to do it? Why we need to understand what exactly failed? Why we need to identify the leak source? First of all, to understand how to fix it. Because currently on the market, there are challengeable solutions on rigless barrier restoration. For tubing leak, it could be a tubing patch, straddle Packer. For a Packer leak, it could be some other new technologies available on the market with, 50-50 chance for success, I would say. Then we also needed for data statistic, for analytic. Because if we see repeating trends on something, we could do something, to prevent. And also for the root cause analysis. So that's the main, let's say, solution for the identification of the root causes. And if we identify root causes, we can prevent them. Yes, we can eliminate them, and similar incidents will never happen again in the whole field. And then after all this is done, after the situation is clear, we can identify the way forward. Either, and there are many options here. Yes, we may immediately kill and secure, send for workover. We may allow this to operate until the workover will be available, or we may apply a regular solution, or we may allow this to operate until the risk level changed, maybe for some reason. If we are very confident in our secondary barrier envelope. If, let's say, the well is brand new, but already the pack early happened, but we are confident in the 9958 casing, or whatever is your production casing is, because it was just cemented, just set and cemented. So we know for sure it cannot get corroded within at least 5 years from now. So we may allow this to operate. But if internally the casing will be exposed to the corrosive environment, that may affect on the corrosion rates, degradation of the casing. Yes? So if we can somehow monitor it, then fine. Now, a little bit about the understanding of the risk, because even here I understand, even within the same company, there is some kind of misalignment, misunderstanding on what the risk is. So what is the risk? It's a combination of something and something. Yes, it's a combination of hazard and activity. Pressure is a hazard. Operating the well, having the well exposed to the pressure is our activity. So if we don't want to have a risk, we can either eliminate the hazard or the activity. Yes. But normally what we do, we'll just install the barriers between the pressure and the exposure area. Surface, or if we have underground aquifers, permeable aquifers, we need to isolate across in between the pressure source, which is our reservoir, and aquifers. Normally there should be a cap rock there, okay? Natural cap rock, if you have pressurized reservoirs. And by the way, the subject of today's discussion is not about wells which are dead, not about the wells which has no pressure at surface, where you use ESP or gas lift or whatever. Okay, it's about wells that can flow naturally, which comply to double barrier policy. So, what is the risk? It's a combination of hazard and activity. And if we try to calculate the risk, what we use? We use severity, which is the consequences, and likelihood, probability. What is the probability of the incident to happen? And that's our initial risk. And then we apply our control measures, prevention and mitigation measures. Prevention reduce the likelihood, and mitigation reduce the severity, the consequences. And then we end up with the residual risk, basically, which is initial risk minus impact of the risk control. So far, so obvious, correct? I mean, there is nothing new I mentioned today so far. So let's try to understand. Here, I have a car, and okay, sorry, there is some animation here, but okay, fine, no problem. Look, if I have a car which is equipped with those safety bags, am I safe or no? This safety bag, it reduces the risk of the car incident, risk of personal injury in case of car incident. But what exactly it affects, probability or severity? You can type in the chat. Those airbags, safety bags, they reduce probability or severity. So what is the difference between mitigation and prevention? Prevention measures, it's measures that aim to reduce the probability of the incident to happen. Mitigation means your incident happened. Assume that your incident happened. Well blowout happened, personal injury, car incident happened. So mitigation is when you apply measures to reduce the damage, reduce the impact of the incident. So basically, yes, those safety bags, airbags, they are designed to reduce the severity of the incident to happen, but they have nothing to do with probability. And sometimes you have the same situation in the well. For example, you have sub B. This is, by the way, this is actual cement bond lock from the well with sub B, with sustained annulus pressure in B annulus, or sustained casing pressure. And I have another log, corrosion log, which shows me that this casing, production casing, get also externally corroded. What can I do to prevent incident here? I don't have access to the outer surface of my production casing. It is cemented. As you can see, not very well cemented. But it is like 3,000 feet underground. What I can do from outside? Nothing. So I have zero prevention measures. I cannot stop it. The only prevention measure of the incident I can do, what I can do now, I can retrieve my tubing, run inside the casing, and do remediation below this potential corrosion leak point. Correct? That's the only prevention or control measure. I cannot do anything. But maybe I have some mitigation measures. What could be my mitigation measures? We can think about it on the next slide. But what I try to say here is, if we talk about the healthy well, which has two barriers, and we are talking about the risks. So the risk will be, in my mind, the failure of primary barrier. And if it happens, I have my secondary barrier. And in this case, in this approach, the secondary barrier is my mitigation. Correct? I assume that I got the loss of primary barrier. It happened. The failure happened. I got the pressure in my A annulus or B annulus. And then my secondary barrier is my mitigation. So just, to stay on the same level of the understanding of what the prevention, what is the mitigation. But the likelihood or the probability of the well blowout to happen if the well is already sub is the confidence in the condition of your casing. If you're 100% confident that your casing is okay, you just tested it recently during the last workover, for example. You did the corrosion look, you related from A to B. You're confident that it can, you tested at 2000 PSI and now your pressure is 500 PSI. And it happened just yesterday. So, you're confident. So basically after you recover all the information from the well history, you discover that it was recently, the barrier was revalidated, retested. You can reduce the probability of the incident to happen. Yes. Now, how we can control the severity of the well blowout? If we think, okay, let's say well blowout happened, what would be our mitigation measures? It happened already. You have a flow, you have a fontaine. Your emergency response. Do you have the emergency response plan? Do you have the resources allocated? Do you have duty people who knows what to do in case it happened? Then you can think about, okay, maybe I can, on the risk assessment, I can reduce my severity level, As per my experience, human factor takes place in such kind of critical situations when people doesn't know exactly what to do, unless you reduce the human factor by setting clear rules and procedures in place. And, such kind of properly done risk assessments, they can improve and support your position in front of the management. Sometimes it happens that you have to explain something to the non-technical people, but get their commitment. So that's how, with the risk assessment, you can show that whatever we have now, it will not reduce the risk, yes, but what we need to implement, what we need to have in place to really achieve a low risk level, acceptable risk level. Sometimes it cannot be done with the prevention, but maybe through the mitigation. So, example of the risk matrix. It could be 3x3, 4x4, 5x5, 6x6. Doesn't really matter. Yes, each company has a right to set up their own risk assessment procedure. And let's say we are talking about case of sub B or sub C. Yes, so we have a pressure coming from the reservoir, production casing set in the reservoir, exposed to pressure during cement setting. During this transition period, pressure migrated, created a channel, and then the outer casing might get corroded externally because it is located across the aquifers, and cementation across the aquifers is not always, let's say, up to the expectations. And we might have a corrosion of certiness rate easily. And we don't know if it will be corroded or no, because we didn't log certiness rate. We don't know what is the condition of certiness rate. So we have zero control on the probability of the failure. And maybe the failure already happened. Maybe you have underground blowout, underground cross flow from reservoir to aquifers or other formations, and you don't know about it. You can do the leak detection log to check if there is any active cross flow. But sometimes we don't have full control on the probability of the incident to happen. Yeah? But we can work on something else, on some other control measures. In this case, periodic surveillance. The best choice would be fiber optic cable, yes, permanently installed that will show everything. Currently, this is available. And response plan, I mean, let's say we confirm that this happened. Are we ready? Do we have the plan, what to do? Do we have resources? Do we have people or service within our contracts that can handle such kind of situation? You know, then we can say, okay, even though it happened, even though it is sub B or C, but we will timely detect it and address. This is an example of the mitigation of, let's say, sub B or sub C cases. What we can see here, we apply heavy brine and we bleed off the pressure, and then we add the brine, bleed off the pressure, add brine periodically several times, and we achieved the situation when the pressure significantly reduced. And as per our risk assessment, we can say that, okay, we reduce the risk. Let's think together. Did we? What exactly did we reduce? Have we reduced? Probability of the failure to happen didn't change. If the outer casing get corroded, that's it. But we reduce the pressure. So it may happen later, not now. Okay? At the moment, we can say yes. By a reduction of the pressure, we, let's say, postpone the incident. Okay? We give it we extend our grace period. Because yes, if your casing, external casing is corroded, there will be a time when it's going at the place of the corrosion, it's going to burst due to internal pressure. Yes, but by decreasing the pressure, we extend the grace period. But again, we don't know unless you know. You can you can judge, you can evaluate, you can consider it, but you need to know what is the corrosion of your casing. Yeah? What is the ultimate wall thickness or metal loss? Now, in terms of the severity, look. Let's say it will happen at surface, and instead of 500 psi, we have only 200 psi. But still, it's going to flow. And all that heavy brine that we injected, and it is not much, honestly speaking, it's going to be flow back. And then we're going to have, again, high pressure. So in terms of severity, I don't think we change something, okay? So, but it's a kind of a control measure which may extend your grace period. And you need to know exactly what you're doing, because that needs continuous human intervention and monitoring. Now, let's think of, we have a sub-well, sub-A scenario, yes, tubing leak. So what could be our prevention measures and what could be our mitigation measures. In mitigation, again, it's easy. I just assume that secondary barrier failed as well. We have a well blowout. So what we're gonna do? Do we have all those measures? Do we have gas detectors, H2S detectors, fire alarm detectors, automatically activated that informs the control room, connected to the maybe a shutdown system that automatically shut down the well, and then there is a clear response plan. There is a team that will be immediately mobilized. The team will be equipped with proper resources to cure the issue. That is our mitigation measures, yes? And obviously, barricade, radio system, everybody aware, there is no one, the area is isolated. So this is our mitigation measures. Prevention measures here, it's all about the condition of our secondary barrier remaining one, honestly speaking. Okay? What is the probability of the incident to happen? It's just a condition of your casing. Just think about it. That's why I spent so much attention at the beginning about casing corrosion. Okay. So that's it, and I can handle the questions now. Before I do this, I want to say here that these are, you can make a screenshot or photo. These are potential subjects for future webinars. Okay. If you see something interesting for you, you can give me a message or put it in the chat box here. So let's go. I will start with the questions in the comments. Okay, okay, so let's go.
Let's take the questions as they came. I'll show them on screen.
Yeah, so Ruslan has a question. Andrey, which proactive steps would you recommend based on your experience to prevent corrosion, especially outer or... Okay, yes, obviously. Look, there are several options on the table. One of them is the most solid, which is use CRA material, yes, stainless steel casing, which is the most expensive, but the most, let's say, solid one, robust, if your company budget allows you. Win-win solution could be coated casings, okay, externally coated casings, and control of your fluids that you use just before cementing. The fluid that gets contaminated with the cement and get trapped in your casing void spaces. Besides pressure testing the casing, what other factors can contribute to cement degradation? Well, it's all about pressure and temperature cycling. But if we're talking about special projects like CO2, yes, if you have CO2, you need to use CO2 resistant cement. If you have high H2S, you need to use H2S resistant cement. But chemical degradation of cement normally doesn't happen in the most of the environment in the oil field industry. So it's normally just pressure and temperature cycling. And could it be that if the cement doesn't hold pressure from the lower formation, it might cause the upper formation to rupture? And in such cases, how can we perform proactive diagnostic if we might not even see any subpressure at surface? Let me try to understand the question. So basically, we don't see any pressure indication at surface, and we have a cement degradation at the bottom, and the pressure from the bottom migrated to the upper through the original cap rock that initially was okay, but since we drilled the well, we created a path and the isolation was not good, and we created communication. Yes, obviously. If it may happen that the formation, which has never been exposed to high pressure, becomes exposed after we drill the well through several formations. It happens, yes, and it gets pressurized. Not really a rupture. Well, I mean, it takes a lot of efforts to create a fracturing, during fracturing operation, we use a lot of units. We create very high flow inside the well. I'd likely it will be a rupture, but yes, the upper formation can be easily get pressurized and may leak further.
So a few questions from me and comments from me,
Sure.
Andrey. Then, what are the typical sources of corrosive fluids that you have seen at ADNOC? So sources in terms of formations and fluids in terms of nature.
Mm-hmm. For the internal barrier, when I'm talking about the tubing corrosion, normally there is no cases of outer tubing corrosion, obviously, because outside we have completion brine, which is inhibited in the anodes. Inside, what really triggers the corrosion is not really H2S. It's a rare case when we really notice H2S or CO2 corrosion, but water is our main enemy. For several tens of years, starting from 1960, carbon steel L80 was our choice of material for the tubing, and it worked well until recently in 2014-13 we start getting water, since we are in the brown phase, and this water changed the situation completely. Now we are in a conversion to other materials. Where we have low H2S environment, we use super satin chrome. In a high H2S environment, we either use nickel alloy like alloy 28, SM2535, or we use carbon steel, but we assume that the workover should be coming soon. Another one.
Okay, and external sources
for the casing.
and
Okay.
type of fluids. Yep.
Yeah. For the casing, we have aquifers, and those aquifers, this is a common problem for the whole Middle East area, Gulf area. So they are very salty. The density is 1.14, 1.16 Sg, and chloride content is 130, 150,000 milligram per liter. So it's much more salty than the seawater. And okay, there is no oxygen originally there, but again, once we drill the well, we introduce oxygen with our drilling mud, which get lost inside those aquifers, but comes back to us, and we get a corrosion. So
and you
that's
do,
a challenge here.
and you do get corrosion when you're not completely cemented, right?
Yes. And arguably, let's say one of the function of cement, a part of hydraulic isolation and casing support, is corrosion protection.
Yeah, of course.
But there is no service company in the world that can guarantee 100% cement displacement, especially in such kind of conditions we have here. I mean, massive aquifers, 2,000 feet aquifer. What is this?
All right. Question from Jose Luis. He's asking about any experience with flow of gas. So annulus charging with gas, but not with liquids. So the difference in mobility, seeing the gas, not seeing any liquids.
Clear. So look, if we're talking about any specific lab tests in terms of cement slurry in the cured condition, permeability against gas and liquid, we are not such kind of cement lab company. Okay, so we don't have such kind of experience. But if you're talking about the wells and the capability of the cement hold the gas and the liquid in the well, okay, we have a clear references like NORSOC standard. Yes, we need at least 30 meters or 50 meters or 150 feet plus minus of good cement confirmed by the circumferential log or Shubin test. Now, why we have migration of the hydrocarbon to surface, whether it's gas or liquid? What we noted in our group of companies is if our casing is set inside the pressurized reservoir, then the migration happens during cement curing period, transition period. Cement loses hydrostatic. It's not liquid. So we have a well-controlled situation behind the casing during cement hardening process. At the same time, it doesn't develop the rock solid strength immediately. It takes hours, yes? So during this transition period, pressure migrates. But if we cement above the reservoir, if our casing shoe point is above the pressurized reservoir, even the cement is really not up to the expectations, still we do not have sub B or sub C. So obviously, gas migration happens much faster than oil. Yes, I agree here. But it's nothing to do with the cement permeability in cured conditions. All this happens during the transition period, before it gets solid. Thank you.
Okay, we have two more questions. So one from Anar about what your experience has been to derate production tubing after patching.
Hi, Anar. Look, there is a theory and there is a practice. There is a equipment working pressure rating provided by the owner of the tubing patch or straddle packer. And then it's up to you. You can, if you need, if you have to, as a minimum, obviously you have to test it to the tubing to the maximum shut-in tubing head pressure you can experience during your well life. Plus, you need to add some extra pressure value for the killing purposes. So we add 500 psi. So I believe that's the minimum. And if your equipment working rating is less than that, then don't even apply. Okay. So
to that,
so let's say
I
we
would
have
add, Andrey, that depending on the position of your patch, you also have to be careful about the collapse case, which could happen, because patches can also conduct the pressure from the annulus to the tubing, depending on your load case, but the collapse resistance is usually
especially
pretty weak.
in the gas producers with high big tubing size. Yes, completion brine is normally quite heavy. There is a gas in the column in the tubing. Yes, agree. Simulation, proper simulation should be done. But again, Anna, it's not really about degrading from original. It's how much you actually have. Okay. Hope I answered. Okay. There is a question
by Mike on the fact that the introduction of heavier fluids in an annulus also offer the option to use some buffered fluids treated for corrosion, etc. So a number of additives that might help address the corrosion situation.
I have to admit here, yes, if you have injectivity and you manage to inject your heavy brine down to the corrosion point, potential leak point, and the issue is internal corrosion of the outer barrier, yes, it can help. Agree.
And then maybe one last comment from myself. You haven't really developed the sort of tools that you have used locally for diagnostics. So you haven't talked about noise logs. You haven't talked about fingerprinting the gas or analyzing the gas, etc. So what's your experience been with that? Or the you showed the lubricate and bleed steps. There are other ways to minimize the number of cycles.
I can answer this question. Thank you, and thank you for this question. It was so basically in terms of the fingerprinting, we have an expert who did a great job in terms of a really deep chemistry analysis of the effluent of B and C. Okay, but honestly speaking, if you look at the lithology of this area, all the pressure sources are located below the caprock. And for me, as a well integrity guy, it doesn't really matter if it's reservoir 1 or reservoir 2 or reservoir X or reservoir Y. Anyway, my curing will be done above it across the caprock. So that fingerprinting, it doesn't really help me. But recently, we had a successful trial. We used 3 fiber optic cables from different service providers, 1 bare cable and 2 coated cables that were used as an intervention. So we didn't install it on the tubing or casing, outer, inner installation. No, we run it inside the tubing, and then the one which is a bare disposable fiber optic cable, it's designed to be cut and get dissolved inside the well. And then the coated cables, yes, we retrieved. So, and plus we used one advanced tool with, let's say, special combination of the acoustic sensors inside this tool. So total 4 different technologies we tried to support our sustained casing pressure investigation, sub-B and sub-C investigation. It is really challenging. Our success rate was very low when we come to the investigation of those sub-B and sub-C cases. So with I can say that all technologies proved to be efficient in different scenarios, because we had different scenarios. We gave them really hard cases of really low pressure values, low leak rates, and also there was one case of the air environment. So the tubing was full of gas at the top, and the air also was full of gas. And you know that acoustic signal really attenuates, difficult to detect in case of gas environment. So, but some technologies managed to do it as well. So this technology is about to be presented internally to the committee. This pilot, let's say, and this pilot will be presented on upcoming ADPEC in Abu Dhabi, who will be in Abu Dhabi this year, very soon, within less than 3 weeks. Most welcome. Third day in the afternoon, there will be a presentation of this pilot.
Very good. Okay, well, we've reached the hour, Andrey. Thank you very much. I'm not sure, Jovan, are you still with us or?
Yeah, I'm here. So from my side, just a quick one, if Andrey can answer, but very briefly, how the industry are dealing with, example, the cementing technologies to prevent sustained casing pressure in depleted reservoir from your experience. Did we have any movement in technology and new stuff which we can tackle? Example, if we face problems during the drilling and we know that cementing operation will be jeopardized, did we have any new technologies which can?
I have to admit the quality of cementing within last years dramatically improved. And even I ask my friends who works in the fields on the rigs, like, guys, what really happened? I mean, why before cementing was that poor and now we get a kind of really big improvement? Look, there are technologies available on the market that can prevent transition of the pressure, migration of the pressure during cement settling process. But up to which limit? Any hard barrier, any valve, any plug has its pressure rating, working pressure rating. Same with the liquid barriers or thixotropic slurries. If we are talking about the migration during cement settling, all of them can handle some specific value, maybe 50 psi, maybe 100 psi maximum, but not 500 psi, for example. It's pressure differential, obviously. So in terms of prevention, sub-B, in those cases where it really happens across, when we have a production casing shoe set inside the pressurized reservoir, cement slurry alone, it's not efficient. Sorry to say this. So our recommendation is to use external mechanical barriers, external casing packers, any type of packers. There are some options available on the market, packers which are coming together with multi-stage tool, DV tool. There are packers, swellable packers, why not? Something better than nothing. Metal to metal annular packers available as well. Okay, if your budget allows, that would be the best option. You can install it in across the previous casing shoe. Depends on your casing design, obviously, yes. But it's also should work. So hope I answer you on. I understand that cementing people will not like my answer, but That's what I mean, I don't have any background to support cement in terms of the gas migration or oil migration during cement setting period. I rely on mechanical barriers.
Yeah, this is a great topic that we will bring somebody who have experience.
And by the way, if you apply mechanical barrier, external casing packer, then you don't need to pump expensive advanced cement slurries, and maybe you can save on cement bond logging. Okay, just throw the ideas. Don't say that I said this.
Thank you, thank you. This is all from
All
my
right.
side.
That's it. Jovan, do you want to say a few words or conclude or mention the upcoming?
I just want to thank Andrey for sharing his experience and willing to share with the SP community. Thank you, Andrey, for your work and time to be with us today. I would like to say that we have upcoming webinar on the similar topic, but we will speak about the cement behind the casing and how much we pressure test the production packers, but to not jeopardize the cement behind. What is the, let's say, to come to the point to define the rule of thumb or to be very close to that and to share experience. We will have a speaker from Schlumberger cementing expert, and we will have a completion expert with us. Stay tuned. We will publish soon the date and the time. So be with us and follow us on LinkedIn and on SP official page. For more information, we will share with community and be with us with our well integrity SP journey.
All right. Thank you. We'll see you next time then.
Thank you, everyone.
You know, people ask me why they should join SPE, and what I tell them is that SPE is absolutely essential. Frankly, if SPE didn't exist, somebody would have to go out and create it. When you graduate with a technical degree, a petroleum engineering degree, or other engineering degree, you get a lot of really good knowledge that gets you started on your career, and you learn a lot on the job. But the jobs that we have in this industry, they're really quite difficult. And you've got to have other resources, either to solve specific problems you might be having at the moment, or to better understand how to solve, daily issues that you work on. SPE provides opportunities to learn about new things that people are working on. There are great articles in JPT magazine and the other magazines that we have that are really useful. If you're not reading JPT every month, I tell you it's essential to do that to keep up with the technology. We have excellent conferences where you can learn from people who have solved very difficult problems in our industry. And doing that is just incredibly important and incredibly useful. To me, I don't see how you can be an engineer working in the petroleum industry and not find value in the resources and the opportunities that SPE provides. It's an opportunity to meet people who can help you in the industry, and it's an opportunity to get the knowledge you need to be successful.